I'm recording now. I am on campus Mondays and Wednesdays, and so I do hold office hours face to face. So, and I do have a Math 1325 face to face on the Northwest Vista campus from 11 to 12:15, but on Monday, Wednesdays. So if that works for you, you are totally welcome to come and sit in on the class. And you know, if you need that face-to-face, or if you want to stay in this one, if this time works for you and days work for you, then come to my office hours and we can work face-to-face on those. So don't feel like you can't come to the campus and see me face-to-face.
Okay, I got you.
Okay. So yeah, so keep me posted how, how this is working, because I realize that sometimes you don't, open up the notes, and so you don't see what happens. So with this class in particular, this is considered a Kerrville class because I live in Kerrville and we have a Kerrville site out here. And so we were trying to do it where it was Zoom for San Antonio students and face-to-face for Kerrville, but everybody is San Antonio. So that's why it's just 100% Zoom.
Okay. No, it's fine. Everything's good.
Okay, very good. All right. So, and I try to keep it as, close to face as I possibly can, but, you can only do so much with technology. So, okay. So, what we're going to do today is we're going to start into the actual calculus material. And so remember where the reactions are. You put your cursor at the bottom. You might have the 3 little dots, and then you'll see reactions. So can you put up a thumbs up if you've ever taken calculus, not pre-calculus, just calculus, like in high school or, an AP class or whatever. Okay, so Cassandra. Okay, so Cassandra, you're the only one. So if you need a study partner and you want to meet with Cassandra and Cassandra's willing, jump in. Reach out to Cassandra because she's going to have information. This will be her second time seeing calculus. So she might have some insight that will be super helpful to you. What I do is, because this calculus class, the STEM version calculus and the business version calculus are 2 completely different things. So it's the same concepts, but we don't use in the business calculus, we don't do any trigonometry. No sine, cosine, tangent, cotangent, none of those are in this class. And so it is a little less intense than the STEM version. So Cassandra, you may have information that you don't need for this particular class. So just kind of be aware of that. And so I treat this class as if this is the first time seeing this information ever, like you've never seen it before in your life. So what we have discovered with math is when you see something the first time, there's disconnects, right? You're going, oh, don't really get it. Then you see it a second time and you go, okay, now my connections are starting to get closer and closer together. And then you see it a third time and you go, oh, okay, now I see the connection. And the more that you practice it, those paths in your brain are going to get smoother and smoother and smoother. Okay. So what all of that entails is you have to practice. You cannot skip the homework. You cannot skip the quizzes and expect to do well on the tests, because all of this is going to take practice. So it just takes time. So you have to make the time in your schedule to sit down, if not every day, at least every other day, to look at the material so that those connections in your brain are going to get smoother and smoother and smoother. And before you know it, you're going to look at a problem and go, oh, I know exactly what I need to do. Okay, so I am recording this. I will post the recordings in class. Sorry. I'm so sorry. My dog thinks that she has to protect me from anything that walks by. It drives me nuts. Okay, so where was I? So you have the class, don't miss a class. You have the class to get your information. You have the Zoom recording to get your information. In Canvas, you have the resources that I post, so you have recordings there. And then in your My Math Lab, you have examples and show me examples. You also have videos. There's other videos in My Math Lab that are available to you. So don't feel like you have to get everything the first time you hear it, because you might not. And there's a good chance that you won't, especially since it's the first time seeing it. So I will take my time and I will try to give you as much information as I can. And that way, when you go to do your homework, you have all these other resources that you should be watching. So even though maybe you just watch a video every day, that's great. At least you're watching it and you're seeing it over and over and over and over again. Okay, so again, it just takes time. So what we're going to do today is we're going to start with what a limit is. So in calculus, there's a huge difference between calculus and algebra. So when you look at this graph, if this was an algebra class, I would say things like, excuse me, like, what is the y value when x is 1? Okay, so it's an actual value. It's at a very particular place. All right, so at x is 1, if I put a point right here, my y value is 2. What's the y value when x is 3? So remember, this is my x, this is my y. So at x is 3, at x is 3, I come up here, and it's about right here. So x is 4 plus some change, right? What's my y value when x is 5? It's this point right here. X is about between -1 and -2. Or if I come over here, what's my y value when x is -6? I come up to the graph and I get my y value is about 3. Those are all algebra. And this chart right here is showing you all the algebra. What is the y value when I plug in a particular x value? Okay, that's algebra. Calculus is different in that we're talking about what are things approaching. So if I bring my fingers together, I'm approaching a certain point. I may not be at that point, but I'm getting very, very, very close to that point. And that's the difference between algebra and calculus. Is calculus is saying, what am I approaching? What am I getting close to? Okay, so when we're looking at these, you're going to have, this is your definition, right? It's very mathy. This is what you would see in a STEM calculus class. All right, it's kind of confusing. You're going, don't really understand what it means. But basically what we're looking for is what's called a limit. And a limit is, what is it approaching? What are my fingers getting close to? Okay, what am I approaching? And that's what a limit is. A limit will always be, get on with this here. A limit will always be a y value. Okay, so it's just new terminology. That's all it is. It's just new terminology. Instead of saying what's the y value, I'll say what's the limit. Okay, so that's what you want to let me get this smaller here. See if it'll let me. No. Okay. All right. So limit just means y value. So a lot of times what happens when you're learning something new is you have to adjust your thinking and go, all right, what does that term actually mean? So a limit just means what's the y value. And so what I'm looking at is there's new notation. I'll move this over a little bit. Okay. So the notation is, you're going to write things this way. The limit as x approaches some value, and we'll call it c, of some function. And then your answer is going to be the y value at this value right here. So mathematically, nothing new is happening. It's just you're looking for the y values, okay? What's changing is the terminology, and not what does it equal, but what is it approaching? What is it getting really, really close to? And it has to be close. It has to come in from both sides in order for a limit to exist. Now, why is this such an important concept? In calculus, we're going to get to something called the derivative, right? And the derivative, again, is just a slope, and I'll say it over and over and over again. It's just another way to say a slope, so another new term. And you cannot have a slope at a graph if the limit does not exist. So that's why we have to know whether a limit exists or not, is because if we're going to find a derivative, the limit has to be there. There has to be a y value there in order for the derivative to exist. Okay, so how does this work? So I'm going to do this both algebraically and graphically. So you're going to have to be able to find limits both in both concepts, algebraically and graphically. So I'm going to put these two together. So here is my function, right? Function is x squared. Well, we know what that is. If I create a table, if my x value is, say, 0, and I plug 0 into this x squared, I get out 0. So here's my point. If I plug in 1, if x is 1, my y value is also going to be 1 because 1 squared is 1. So I put a point right here. If I put in the value 2, what's my y value? What's my x squared going to be? It would be 4 because 2 squared is 4. So I'm going to put a point right here. So you can see it's starting to grow, right? If I put in x is 3, 3 squared is 9. So I'm going to put when x is 3, y is 9. And I'll do just a few more. What if I put in a -1? Well, when I look at this graph, I'm only looking at values that are positive. So if I do this, -1 squared is 1. I could put a point here, but I really am only looking on the right side because this tells me where to look. If I'm looking at x is approaching 3, then all I want to look at is at that particular point. Okay, so if I do one more, if I do one more, if x is 4, then my y is 16, and you can see it's going to be all the way up here. Okay, so the graph part that I'm looking at is right here. You're going to pretend that is a beautiful parabola. Okay, so when I look at this graphically, if I'm looking, pretend that I am bringing my fingers down that graph, and my fingers are coming together. When I look at x is 3, my fingers are coming together. I'll do a different color here. So pretend like these are my fingers. Okay, my fingers are coming together. This is my right hand. This is my left hand. Okay, and they're coming together, and I'm going to meet right there at x is 9 or y is 9. So the limit as x approaches 3, so here's my x is 3, I'm going to come up to my graph and look, is my y value of 9 or the limit of 9. So graphically, you're looking at where do your fingers come together? That's what you're looking at graphically. When I do this algebraically, I literally just plug and chug. I plug this value into my expression. I get 3 squared equals 9. So mathematically, all you're doing is plugging in the value and calculating. That's it, chugging out an answer. Okay? Any questions so far? Okay, so let's try a couple. So here's all the rules of limits. Now, obviously, in this class, I am not going to spend a lot of time doing the STEM version of calculus, right? This is just certain rules, and I'm going to show you how these rules work instead of trying to go through and look at this and go, holy crap, what does this mean? Okay, I'll explain all of this as we work through them. Okay, so if I have, let's look at number 3. If I have the limit, so this is how you read it, the limit as x approaches 5 of this function, 2x squared minus 8x plus 3, all I'm going to do is every time I see an x, I'm going to plug in a 5. So this is finding limits algebraically. Okay, and it's literally plug and chug. So where do these rules come in? Well, right here, if you look at 4 and 5, this is saying if I have a function plus a function, so this 2x squared could be this part, the negative 8x could be this part, all I'm doing is I'm finding the limits at every single term. So what does that mean practically? Well, I plug in 5 every time I see an x, and I calculate. Excuse me, so 2 times 25 minus 40 plus 3. So the y value, the limit, as x approaches 5 on this particular function is 10 plus 3 is 13. Okay, now what does that look like graphically? So let me get to Desmos. So Desmos is a great tool. It's a great tool. It is a graphing calculator that works really, really well. All I have to do is type in my function. Was it plus 3? I always forget what it is. Yeah, plus 3. Okay, and it graphs it for me. Now, here is my caveat. I don't mind if you use Desmos to make sure that your mathematical process makes sense. Okay, that's going to be really important. This is not a tool to use to find the answers. This is a tool that you use to make sure your answers make sense. Okay, big difference, huge, huge difference. All right, so let's look at this. It said, let me write this down here, the limit as x approaches 5 of this function, and mathematically, right, algebraically, we plugged it in and we figured it out to be 13. So let's look at it graphically. So here's 2, 4, 6, 8, 10. So 2, 4, here's 5 right here. I come up here and it's right about here. Well, when I come over here to my y value, this is about 13. So your algebraic version and the graphic version should be identical. You should always be able to get the exact same answers, whether you do it algebraically or whether you do it graphically. All right, and you need to be able to go between both of those. Okay, so any questions on that? Okay, so let's stick with just algebraically. Okay, so again, we're going to plug this in anytime I see an x and then calculate. So in the chat, in your chat, type what you think the limit is. What is the y value when you plug in 4? Okay, we're getting some answers. Good. Okay, so when I plug in 4, 29 minus 4 is 25. The square root of 25 is 5. Now, it's also negative 5, but because negative 5 times negative 5 is also 25. But because there's no negative sign in front, then we're good to go. We're going to use what's called the principal answer. Okay, so good job. All right, next one. Try number 5 and tell me what you get when you plug it in. And go ahead and put in chat what you think it is. Okay, I'm seeing some zeros. So you're not completely wrong, just not all the way right. I don't know if that's a thing or not. All right, so let's try this. Let's see what else we got up here. Okay, so Cassandra says 1. Okay, so let's try it. All right, so again, this is always your first go-to. Okay, you're just chugging in, or chugging out the answer. So when I plug in 4, I get 4 squared minus 16, which is 16 minus 16, which is 0. That's on top. When I plug in 4 on the bottom, I get 4 minus 4, which is also 0. This is a big problem. This is what's called the indeterminate form. Okay, so what happens when you have something called indeterminate form, what this screams at you, and I'm going to use red, is that it needs more work. Okay, so what this isn't 0 because I have a 0 on the bottom. When I have 0 on the bottom, that is undefined. 0 over 0 is just called indeterminate form, which means that there's something going on within this function that I can clean it up. So remember I said the first week of class that factoring is going to come in and it's going to haunt you and it's going to come in periodically. So you have to be aware of when to factor. So when you get indeterminate form, this means you need to factor. Okay, and simplify. So going back to x squared minus 16, this is what's called a difference of two squares. Okay, difference of two squares. So I'm going to factor the top. So remember, difference of two squares, it's square root of the first, square root of the second, one's positive, one's negative, over the bottom. And you can see now, oh, I can cancel that. So this whole function is actually the limit as x approaches 4 of the function x plus 4. And now, so now, Cassandra, you're correct. When I plug the 4 in, I get 8. So this is the limit. So let me show you on Desmos what that actually looks like. And I'm literally just typing this in. I am using parentheses so that it will set it up like this. But do you see how it just creates a line? When this gets simplified to the base version, it's just x plus 4. Well, the 4 is right here. That's your y-intercept. The slope is 1, which means it goes up 1 over 1, up 1 over 1, up 1 over 1. So that is just the slope of this line. So at x is 4, which is right here. Here's my 4. Oops. Here's my 4. I come up. There is the point at 8. Okay, so the limit. So again, think of my fingers as coming down both sides. I'm going to change my color here. So my fingers are coming down both sides of my graph, and it's heading towards x is 4, and it's coming together. My fingers are coming together at the y value y is 8, or the limit is 8. So it's approaching that value. Okay. All right, so anytime you have, get out of this, anytime you have a function, I need to erase all this, get that stuff out of the way, hang on. Okay, anytime you have a function where it looks like a fraction, you have to test it, right? Because you're just gonna plug in and chug, and you can do it mentally. So if x is approaching 2, I'm going to plug 2 in here. So 3 times 2 is 6. 6 minus 6, I get 0 on top. 2 squared is 4. 4 plus 10 is 14 minus 14. So this is the needs more work. So now I'm going to factor. Okay, so this is greatest common factor on top. It has a 3 in common. Okay, and then factoring on the bottom. So remember, what do you multiply to get 14, add to get 5? Or I'm sorry, negative 14, add to get 5. So it's going to be a negative 2 and a positive 7. So this bottom factors out to x minus 2, x plus 7. So again, there's my 0 over 0. I'm able to get rid of that indeterminate form. So now I have the limit as x approaches 2 of the function 3 over x plus 7. I plug in my 2. I get 3 over 9, which is 1/3. That's the limit. Okay, so there is a value sitting there when x is 2. Okay, so any questions so far? Okay, all right, so algebraically, limits are not too bad. You plug in the value, you chug out the answer. If it's 0 over 0, you've got a factor. And then you're going to cancel, and then you'll plug in the value of the simplified function. Okay, now this one right here, I wanted to show you real quick because there may come a time that you'll see these. Remember fractional exponents. Okay, fractional exponents. This 1/2 here is an exponent. So this is actually, I can write it as 1/2 times 36. So this is a number times 36. And then this is actually the square root of 36. So this goes back to that review of being able to go back and forth between fractional exponents and radicals. So then you can simplify. So half of 36 is 18. Square root of 36 is 6. So 18 minus 6 is 12. So that's the limit as x approaches 36 of this function. So just remember, there's things that pop in quite often. One is factoring in this class, and the other one is fractional exponents. And we actually use those a ton towards the end of chapter 9. So you'll get super comfortable with fractions and exponents. Okay, all right, so this is algebraic finding limits. Okay, now we're going to find limits graphically. So we're going to look at graphs and go, okay, what is the limit? What is the value approaching? All right, so think about where am I heading towards? All right, so there's something called right and left-handed limits. Okay, so if I asked you to look at this graph and I said, what is the limit when x is approaching 2? Well, remember, a limit only exists when my fingers come together. Okay, if I were putting my fingers, and this is where this works a lot better in face-to-face, so you have to kind of imagine with me. If my fingers are on both of these graphs, you can see that they're not coming together. They're 2 inches apart or 4 inches apart, whatever it is. They're not coming together. So at this particular value right here at x is 2, my fingers don't come together. So there is no limit, because remember, a limit means it comes together from both sides. But we can have limits right side and left side. Okay, so how does that look? So if you have a left-handed limit, you're going to have a minus sign after the value that you're approaching. So look right here on A, see how there's a negative or a minus sign after the number? So again, it has nothing to do with positive or negative. It just has to do with which side am I coming from. So the left-handed limit, think left hand. That's why it's left-handed limit. That means I am coming in from the left side. So I'm coming in from the negative side. That's why there's a negative there. Okay, so when I'm looking at this, if I'm coming in to X is 2 from the left side, right, from this side, I am heading towards the Y value of 1. So I do have a left-handed limit. Okay, I do have a value that I'm approaching. And it's a solid value, it's a solid number, so I'm good to go. Okay, but I am approaching Y is 1. Okay, the other side is what's called a right-handed limit, and there's a plus sign there. Okay, so when you see the plus sign, that means you are coming in to X is 2 from the positive side. So with my right hand. Okay, so I'm coming in from the positive side. So with this one on the right side, I am heading towards 2. Well, that makes sense because from the left side, I'm coming and I'm hitting a low value. From the right side, I'm hitting a higher value. Okay, so that does make sense. The left-handed limit is less than the right-handed limit. Okay, and so I'm not coming together. I'm not coming to the exact same place. Now, the other thing to notice is from the left side, there's this open circle, right? We all know an open circle means there's no value there. But that's the beauty of calculus. Calculus doesn't care if there's an actual value there. Calculus only cares what is it heading towards. I am heading towards Y is 2. Doesn't equal 2, but I'm heading towards that value. I'm getting really, really, really close to 2. Okay? So the key, is when you have a right-handed limit and a left-handed limit that are different, notice on C, there is no plus or minus. So if there's no plus or minus, what that's saying is I'm coming from both sides. Well, clearly, I need to get this clear. Clearly, I am not coming to the same value. Okay, graphically, it shows it right here. I'm not coming to the same value. Algebraically, or what my limit are, it also shows that I'm not coming to the same value. So what that means is my limit does not exist. And we use the abbreviation DNE. Okay, so for a limit to exist, the right-handed limit and the left-handed limit has to be the same. If they are not the same, then there's no limit that exists there. And what that means is I can't have a derivative there. I can't have a slope right at that point. All right. Now the other thing, let me stop. Any questions? Give me a thumbs up if you're okay so far. Okay. Okay, we got a few. Use those reactions. I want to, this also makes me know that you are paying attention. You're not sleeping, you're not laying in bed, drinking a cup of coffee. Okay, perfect. Okay. So for a limit to exist, the right hand and the left hand have to be heading towards the same value. But I can have a left-handed limit and I can have a right-handed limit. But if they're not the same, then the limit does not exist at that point coming from both sides. Okay? All right. So I'm going to skip over because the good news, I know you guys have 3 assignments due today or due Monday, but 9-1 and 9-3 are basically the same thing. Okay? So let me give you an example. We're going to stay with the graphing of right and left-handed limits. And then I'll go back to the piecewise functions. Okay, so when you look at this, this first graph right here on the left, okay, this is, if I were to write the terminology, it's x, or the limit as x approaches the value c of whatever this function is. Is there a limit there? Okay, well, this is just, excuse me, just like the one we just saw, right? My left hand, try and keep my colors the same. My left hand is coming here. My right hand is coming from this side. So you can see I'm coming to two different places, right? So what this means is this function is discontinuous. And the limit does not exist because I'm not coming to the same place. Okay, so it's discontinuous there. Over here on this one, on the right side, if I come in from the right, oops, I'm heading to here. If I'm coming on the left, I'm also heading to the same place, right? So this one, the limit does exist. It exists right here, okay, because I'm approaching it. Now, there is an open circle there. Open circle doesn't matter. I am coming to the exact same place, right? I'm heading towards that open circle from both sides. So I'm good there. The limit does exist there, all right? Now, is it continuous? No, because there's a hole there. That hole means there's a jump. So it is not continuous. Continuous means that it is smooth. My pencil or my finger never lifts up off of my graph. Okay, so there's no jumps, there's no breaks, there's no holes. That's what continuous would be. Okay, so when I look at the graphs, this is something that a lot of students struggle with because they look at this graph and they go, holy crap, this is a lot, right? So what I want you to do is I want you to focus your attention only at the value -1. That's the only place I want you to look. So we are going to look, here is my -1. We are going to look right here. We don't care anything about anything else except right here. That's where I want you to focus. Okay, so here we go. This is saying left-handed limit. So I'm coming in from the left side. Where am I heading towards? What's my y value? Should be right here. So I'm heading towards 3. You see it? If I'm coming in from the right side, I'm also heading towards the value 3. Okay, so again, the right side means there's a plus sign. Okay, do you see how these are the same? Well, that means that the limit does exist at 3. So I'm good. As long as these are the same, I am good here. The limit does exist there. But then here is my algebra question. What does it actually equal? So remember, the algebra says at -1, what does the value actually equal? Well, that's where the solid line or the solid dot comes in, right there. It actually equals -1. Okay, so in this case, yes, we do have a limit. We do have a value that exists at -1, and it equals -1. It's this value right here. But is it continuous at -1? Well, because there's a gap here, right? It would be like if I am walking along this graph, I have to jump down to the dot, the solid dot, and then I have to jump back up. So there is a gap there. So this is not continuous or discontinuous at -1. Okay, so for something to be continuous, it has to have a limit. Okay, so there's 3 things that you want to check off. The limit has to exist. Okay, well, that checks. We're good. We have to have a value at the point. Well, that works. Okay, but the third rule means that the limit has to equal the value. Well, in this case, our limit does not equal our value. Our limit is 3 and our value that it equals is -1. So this one doesn't work. So that's why this is not continuous, or you can say it's discontinuous. Okay, so these 3 rules are what's called continuity. It's just a fancy word meaning, is it smooth and continuous? So that means our graph has to be smooth and continuous. In other words, if I were to graph something, my pen would or pencil would never lift off that graph. Doesn't matter how many curves, how many dips, how many high points, it will never lift off my graph. Okay, so these 3 things have to happen for it to have continuity. But you can also just look at it and go, well, there's a hole there. So no, it's not continuous. It's not smooth and continuous. Okay, so any questions on that? All right, so now we're going to use the same graph. Let me erase all my writings on here. Okay, we're going to use the same graph. But now notice what we're looking at. We are only looking at x is 1. So we are only looking right here. We don't care what goes on over here. We don't care what goes on over here. All we care about is right there at +1. So you really have to train yourself that when you're looking at a graph, you only look at the spot that your x is approaching. Don't worry about anything else. Just only look at the spot where the graph is approaching. So here we go. Coming in from the left, I'm approaching 1. Here's my 1 right there. So I'm coming in from the left. I'm approaching 1. The limit does exist there. It's at 1. So I'm approaching this value right here. Okay, now I'm going to come in from the right. And notice I don't care about this. I don't care about this graph over here. I'm coming in from the right and I'm only focusing when x is 1. So at this one, it also equals 1. Okay, so again, these are the same. So I do have a limit that exists at 1. What does it actually equal? Well, there's a solid dot here. So it does actually equal 1. Okay, so going over those rules again, we have a limit that exists. We're good there. We have a value that exists. And with this one, the value and the limit are the same. So we're good. We've checked off all 3 rules. So because these are the same, then yes, this is continuous at x equals 1. And you can see it, right? Right at this point, my pencil never leaves the graph. Okay, thank you, Brian. Okay. All right, any questions? So what you're seeing, I'm sorry, I ask a question, then I jump right in. Any questions? Anything that you need clarity on?
For the rules on top where you had them, that check off list. What was number 2?
Number 2 was you have to have a value at the point. So
At-
this is this, yeah, this question right here. Is there an actual value at that point? So like on this one, yes, there is a value, but the value is down here at -1 because it's a solid dot, where up here it's an open circle. So there is no value right there. The value is down here. Where on the second one, this one, the value at +1, it was a solid dot right here, is +1. So there is an actual value there.
So because it's open, its actual value is 100. It's
Yeah, if it's open, there is no value there. If it's closed, that's the actual value.
oh, okay.
Okay, so the closed dot is the value. The open dot just means that there's nothing right at that point, but there is stuff going on around it. Okay. All right, so I'm going to erase this again. Get all rid of all this stuff. We're going to use the exact same graph again. Okay, no problem, George. But now with example 3, now we are looking at only where x is 2. Let me see if I can bring this down a little bit so we can see it all. Okay. Okay, so look at your graph. Only look where x is 2. And let's see if we can walk through this. So we're going to look where x is 2. We're coming in from the left. So again, we're only seeing, get the right color here. We're only looking right here. My dog's gonna bark again. Katie. Right? All right, so we're coming into 2. Here's 2 right here. Okay, so coming in from the left, I'm looking right here. So someone give me, what's my limit? Coming in from the left.
Two.
Mm-hmm. Perfect. Okay, because it's right here. It's 2. Good. Thank you, Cassandra. Okay. Now coming in from the right. Okay. We got 2 people saying 3. Everyone agree with that? So this is our 1, 2, 3. Okay. So do you see how example 1 and example 2, the right and the left, were the same values? Well, when I look at that, that automatically tells me that my limit exists. With this one, these are different. So they are not going to the same point. So you immediately know that your limit does not exist. The only way for C to have a value is if these 2 numbers are the same. So because these are not the same, your limit does not exist. So what that does is it kills our checklist, right? We just annihilated that first rule that the limit has to exist. So what that tells you right away is this is a discontinuous function at x is 2. Okay. What does it actually equal? There is a value. The value that it actually equals is right here. It's your solid dot right there. So it does actually equal 3, but the limit doesn't exist. So it knocks out those 3 rules. So that you can automatically answer that last question, that it's discontinuous as soon as you see that there's no limit there. Okay. All right, go ahead and try example 4. So now again, we're looking at a completely different spot on my graph. We're looking at x is 3, so right in here. So go ahead in the chat and give me your 5 answers. First answer is limit coming in from the left. Second answer is the limit coming in from the right. Third answer is, does the limit exist? What's the value there? And then, is it continuous? So give me 5 answers in your chat. I'm just double checking, making sure I have everybody on my list. Yep. All right. Let's see. So I have a few answers. Good. I'll wait for a few more. So go ahead and write your answers in the chat. So A is the first one, and then just you don't have to label them. Just give me your 5 answers. Very good. Okay, so here we go. Coming in from the left, and I hope this helps with the color coordination. Coming in from the left, I'm only approaching 3, and I'm heading towards 4. And then the other side, I'm coming in from the right. And again, I'm approaching the same value, which is 4. So because these are the same, my limit does exist, so we're good there. Okay. Does it have a value at 3? Well, right at x is 3, there's no solid dots. So this is, you can use it does not exist, NA, however you want to write it. It's not 0, because if it was 0, then we'd have a solid dot right there. Okay, so because there's no solid dot right at x is 3, there's no answer for it. Is it discontinuous? Yes, because there's no value at x is 3, it kills that rule. So this is discontinuous. And there's a hole here. So if I'm going along with my pencil, I have to jump off the graph and jump back on to continue. So it is not smooth and continuous. Okay. All right. Any questions on the graphing? So this is finding limits graphically. Is it continuous at that point? The importance of that is you cannot have a derivative unless your function is continuous. Okay, so that's the basic foundation for finding derivatives. Okay, so what I want to do now is I'm going to jump back to 9.1 and we're going to look at these, what these are called piecewise functions. It's just a fancy name for you have a function in pieces. That's all it is. Okay, so we have two functions. The first one is a line. And so I'm going to show you this on Desmos. So x minus 5, get rid of these. Okay, so x minus 5, that's our first function. And the second one was 3x minus 4. Okay, so the red line is our first one. The blue line is our second one. Where this cuts off is at 4. So you will only use x minus 5 on all values less than 4. So what that looks like on Desmos, let me see if I can do this. So the red line is x minus 4, so 2, 4, so right here. So you have a solid dot, pencil here, you have a solid dot right here. And it's all these values. So it's all the line, this line going that way. What that means is that all of this is gone. So you need to just kind of ignore that. On the blue line, it's all the values greater than 4. I don't believe. Yeah, greater than 4. So it's going to be an open circle. So here's 4. So it's going to be an open circle and it's all the values going this way. And so this part is gone. Okay. So what we have, if I were to draw this, is I have at 4 here, I have a graph at 8 and it goes up. And then the other one starts here at -1. I'm going to change colors here. At -1. And it's a solid dot and it goes that way. Okay, so it's a graph in pieces. That's all it is. So if visually, if you need a graph to visually see this, that's completely okay. You can do that. You don't have to have the graph. Okay, when you're doing a piecewise function, you don't have to have the graph. But for some, it helps. Sometimes it helps to be able to see it. So coming back to this, so this is, again, piecewise function. I'll go ahead and draw it real quick. So this was at, I'll do this at 4 here. And we have -1 here and +8 here. Now, where did I come up with -1 and 8? Well, all I did is plug this in. When I plug 4 into here, I get 4 minus 5 equals -1. Okay, that's where I found that -1. So it is a solid dot, and it goes something like that. Okay, so all the values less than 4, less than and equal to 4. And then for this one, at 4, it's a +8, but it's an open circle because there's no equal sign, and it goes something like that. Okay, so there's what we're looking at graphically. All right, now if you don't use the graph, you can just use your functions. So when you look at this, remember the right and left. So this is coming in from the left. So this means that you will only use the less than sign. Okay, because you're coming in from the left, you're coming in from values that are less than 4. So the left-hand limit will be connected with the less than sign. So all I have to do is plug and chug. Plug in my value when x approaches 4. I'm going to plug in 4 into the correct function and get -1. So my limit is -1. And graphically, it makes sense. If I'm coming in from the left, I'm heading towards -1. Okay, if I'm coming in from the right, I am looking at the greater than sign, because it's all values that are greater than. So graphically, I'm coming in this way. I'm heading towards 4. So I am heading towards, I'm going to plug in the 4 into the correct function. 12 minus 4 is 8. So my limit is 8. And you can see right here, I'm heading towards 8. Okay, so this goes right back to my left-handed limit and my right-handed limit are not the same, which means that the limit does not exist. So the right and the left always have to be the same in order for my limit to exist from both sides. And remember, there's no plus or minus, so that's asking from both sides. Okay, so that's being able to do this with a piecewise function. And the key is knowing which graph or which function do I use, because these are two different functions. So I need to be able to see which functions do I use. Okay, so jumping to 9.3. Am I going too fast? Do I need to slow down? We good? Let me know. All right, so going to, this is the last part. So going to 9.3. So you can see how 9.3 and 9.1 are just kind of intermingled. They just go back and forth. It's all the same content. The only difference between 9.1 and 9.3 is 9.3 throws in the continuity question. All right, so here we go. And I'm not going to graph it this time. We're just going to look at this and go, okay, which one do we work at or do we look at? So when it asks for, is it continuous or what's the point of discontinuity? I use these values. Okay, so I'm going to start with the left-handed limit. So the limit as x approaches 1 from the left, I use my less than sign of my function. So I'm going to use this top one. So 1 squared is 1. Okay, so the limit from the left side is 1. Now the limit from the right side, I'm going to use my greater than sign. So the limit as x approaches 1 from the positive side or the right side of my function. So now I'm going to use the second function. So 2 times 1 is 2. So you can see these are not the same. I'm not going to the same place. So the limit as x approaches 1 from both sides of my function does not exist. So that means it is discontinuous at x equals 1. So basically, when you're given an example like this, and you'll see this on your My Math Lab, when you're given an example like this, just use these parameters that they give you, the less than or greater than, use those parameters, test each graph or each function. If they're the same, then the limit does exist and it's continuous. If they're different, then it's discontinuous at that point. So all of this, you're doing the exact same thing, just sometimes you have to know when to do it. Okay, so we're going to do it one more time using a different value this time. Now we're using 2. So coming in from the left side, I'm going to use the less than. So kind of connect that less than left side. They both start with L. That kind of gives you a quick and easy way to know which one to use. So because this is my less than, I'm going to do 2 squared is 4. So that's the limit from the left side. Then I'm going to do the limit from the right side. Which is my greater than sign. So it's 2 times 2, which is also 4. So we have a limit. The limit as x approaches 2 of my function does equal 4 because these are the same. So this one, at this point, at x is 2, it is continuous. Now, going back to those 3 continuity rules, there is a value that does exist at x is 2 because of this equal sign right here. So there is a value that exists there, and it is 4, right? 2 squared is 4. They are the same. So you can look at it this way. F at 2 does equal 4. Since these are the same, and since the limit does exist, that's another indicator that this is continuous at x is 2. Okay. Okay, let me double check on one. I don't think there's anything else. Nope. Okay, so here's what you learned today. You learned what a limit is, okay? And so the simple version is a limit is a y value. That's all it is. Just another term for a y value, okay? You learned where a function is continuous or discontinuous. If there's a gap, a hole, a jump, then it's discontinuous. You learned right-handed limits and left-handed limits. And you learned the algebra question of what is actually sitting there, okay? And then you learned algebraic limits and you learned graphic limits, okay? So you did learn a lot, but the good news is they are all intertwined. 9.1 and 9.3 are basically the same concept. The only difference is 9.3 talks about continuity. Okay, so any questions at all?
No, I was just gonna say it does sound like a lot and it looks like a lot, but like they kind of went hand in hand, so you could like follow.
Yes, yeah, and that's always something that I want to try to connect for you guys, is that a lot of times you see a whole bunch of stuff and you go, oh, it's all interconnected, right? There isn't like a new topic. All of these are not new topics. They're just all interconnected. Okay, so on the Thursday, what we're going to do is talk about the actual derivative, and we'll get back into the difference quotient. We'll practice. And then the good news is 9.5, I'm going to show you and teach you all of the shortcuts. So Cassandra, that's going to be hard for you to not use the shortcuts on 9.4. So just bear with me, just one more section, and then we'll get to the shortcuts of differentiation. Okay. All right, guys, that's it for today. I will see you Thursday. Thanks for showing up. Get your homework
See you,
done.
man.
Have a nice day.
All right. Thank you.